Hello everyone, welcome to the channel VLSI Point. This is our second video of playlist Digital Electronics. So without further delay, let's get started. Question number 1. Consider a Boolean gate D where the output Y is related to the inputs A and B as Y equals to A plus B bar, where plus denotes logical OR operation. The Boolean inputs 0 and 1 are also available separately using instances of only D gates and 0 and 1 as inputs. Select the correct options. We'll see the options. First is NAND logic can be implemented. Second, OR logic. Third, NOR logic. Final, AND logic. So let's see the question, what it is saying. They have given one gate as Y equals to A plus B bar, and we have available 0 and 1 inputs. So using those two things, we have to implement some logic gates. In the options, they have given like NAND, OR, NOR, AND. So we have to implement the logic gates using the available options. Okay, let's see how we can solve this question. So we have noted down f equals to a plus b bar, and we are just keeping a as 0 in the function. So if you keep a as 0, simply we are getting f equals to b bar. It's nothing but NOT gate. Okay, so without the options they have provided, we implemented NOT. Next is we have just taken this particular b bar as a b. So b bar of bar means only b. Okay, so f equals to a plus b. So basically we are getting OR gate. Okay, so once we have NOT gate and OR gate, easily we can form NOR gate. Okay, and NOR is a universal gate. So once you have NOR gate, you can implement all the gates. Okay, so the concept of universal gate, as you know, we can implement all the other logic gates using the universal gate. So here we have found out that we can implement the NOR gate, and hence all other gates can be implemented. So options all. Okay, let's go to question number 2. The minimum number of 2 input NAND gates required to implement 2 input XOR gate is. Options are 4, 5, 6, 7. So basically we have 2 input NAND gates available, and using that we have to form XOR logic gate. But the condition is we have to use minimum number of those NAND gates. Okay, so let's see how we can do that. Okay, so this is a pictorial representation of XOR gate using NAND gate. Okay, so the basically if you see we can implement with 4 number of NAND gates. Okay, so just to prove, you can see over here C is nothing but the output of first gate, that is A into B bar, first NAND gate. D is nothing but C dot A bar. Okay, it is, if you keep C as AB bar, you will get AB plus A bar. If you see E is output of this third NAND gate, is nothing but CB bar. If you keep C as AB bar, you will get AB plus B bar, and Y is nothing but D into E whole bar. Okay, so we are just solving this equation. We know Y is equals to D into E bar. This is D, this is E, DE bar. Then what's D? We know it is AB plus A bar. What is E? It is AB plus B bar. So we are solving this, and once you solve, we are getting this term A bar, AB bar, A bar B, and BB bar. So A into A bar is 0. We can cancel out the highlighted term. B into B bar same. So what is left? A into B bar plus A bar B. So Y is equals to AB bar plus A bar B is the solution. It is nothing but XOR gate. So basically we can implement the XOR gate using NAND gates. Minimum number required is 4. So at least 4 NAND gates should be necessary. So option A is our answer. Okay. So question number 3. The output of combinational circuit given below is. So Y is the output over here, and they have provided A, B, C, and we have to just find out what's the output. So options are A plus B plus C, A in bracket B plus C, B in bracket C plus A, C in bracket A plus B. So we can solve this. Just I have numbered all those gates. So just solving, D is nothing but A into B, output of this AND gate. E is nothing but B into C, output of the second AND gate. F is equals to CD, and we know the D is nothing but AB. So C into AB means ABC, and G is nothing but XOR of D and E. D and E. D we have a E also. So by solving, we know DE bar plus D bar E is nothing but XOR. So we have just kept the values of D, E over the equations. We are getting this term. B bar is nothing but 0, because B into B bar or anything into that bar is 0. So we are cancelling this first term. Next is B bar BC. As mentioned, this is also 0. So we are cancelling. We are left with ABC bar plus A bar BC. Okay. So we got G. G is nothing but ABC bar plus A bar BC. We know Y is nothing but F and F XOR with G. You can see in the diagram. Y is nothing but XOR of F and G. We know we have calculated G as this term and F is ABC. We are just keeping in the equation. We are getting two terms. ABC bar into G. Second is ABC into G bar. Okay, this is second term. I have highlighted. So we can solve individual terms. If you solve this one, I have given the solution over here, is nothing but A bar BC plus ABC bar. If you solve this thing, you will get ABC. Okay, so we have 1 as this term, 2 as this term. So Y is nothing but addition of these two. So A bar BC plus ABC bar plus ABC. Just take out B common. You will get this term. By solving further, we will get answer as B in bracket C plus A. B in bracket C plus A. Okay, so which is option C. Question number 4. In the circuit shown, diodes D1, D2 and D3 are ideal, and the inputs D1, D2, D3 are 0 volt for logic 0 and 10 volt for logic 1. What logic gate does the circuit represent? So basically they have provided a circuit having some diodes, one resistor, one voltage source as 10 volt. Resistor value is 1K, and they are saying if the logic is 0 volt means logic 0, if it is 10 volt the logic is 1. So we have to find out by solving this which logic gate this circuit represent. First is 3 input OR gate, NOR gate, AND gate and XOR gate. Let's solve the question. Basically here, as they mentioned, 0 volts as 0 logic and 10 volts as 1 logic. We know if E1 or E2 or E3 is 0 volt, the diode will turn on. Okay, see here, if it is 0 volt, right? So the negative terminal of diode having 0 and this terminal having some higher voltage. Okay, so this diode will turn on. Same for E2, same for E3. Okay, so V0 is 0 volt. Okay, we know V0 is E in the first case. Okay, so E0 is nothing but E. Now consider if E1 equals to E2 equals to 10 volt. Okay, so we are just considering all the voltages as 10 volt. Okay, so the current across 1K resistor is 0 ampere. Okay, if you just keep E1 10 volt, here also if it is 10 volt, this is getting current flowing through the 1K resistor is 0 ampere. Okay, so V0 is becoming 10 volt. Directly this diode gets short circuit because here it is 10 volt. So directly 10 volt will come up here at this V0. So V0 is becoming 10 volt. So if you write the truth table, so for the 0, 0, 0, output is 0 volt. We have seen, right? If any of E1, E2, E3 is 0 volt, output is 0. Okay, if one of the in this case you can see E1 is 1, E2 is 1, E3 is 0. So your output is 0. But the case where all the diodes are getting on, right? That time your V0 is getting 1, that is 10 volt. So this truth table is a 3 input AND gate truth table. Okay, so here just remember the concept that here all the input should be high so that our voltage will become high. Got it? That is the concept. So answer is AND gate. Option C. Question number 5. In the figure shown, the output is required to be Y is equals to AB plus C bar D bar. The gates G1 and G2 must be respectively. NOR or NAND, NAND or AND NAND. Okay. So we have the circuit where we have A, B, C, D as inputs. They have given some gates, two inverters, one NOR gate, and we don't know what is G1 and G2, but we know what Y should be. So Y should be AB plus C bar D bar. Okay, so we can go in the reverse manner. Let's solve the question. Okay, so they have provided Y should be AB plus C bar D bar. This is equation number 1. Okay, but you can clearly see from here is Y is nothing but whatever the F equation is there. Okay, some G2 operation and E. We don't know what is G2. So Y is equals to F some G2 operation into E. So if you compare 1 and 2, it's very clear, right? F is nothing but C plus D bar. Okay, you can see here C plus D bar, nothing but C bar D bar. Okay, so one of the terms we are getting as C bar D bar. Here it is clear, right? So obviously E should be AB, correct? So E is AB. So E is nothing but A bar. Okay, you can see here A bar, some G1 operation and this B bar. Okay, so E is nothing but you can see over here A bar, some G1 operation B bar. Okay, but this equation number 3, if you see it is AB, this is A bar, some G1 operation B bar. So those two equations should be equal. So if G1 is NOR gate, okay, just consider G1 as NOR gate, you are getting A bar plus B bar whole bar, nothing but A bar bar into B bar bar is nothing but AB. So we are getting here G1 is NOR gate, and it is very clear that G2 is simply OR gate. Okay, because it is nothing but just it's doing the addition. Okay, so we'll see the answer. Option A. Let's move to the question number 6. In the circuit shown below, if C is 0, then we have to find the output, that is expression for Y. Options are Y is equals to AB bar plus A bar B, Y is equals to A plus B, Y is equals to A bar B bar, Y is equals to AB. Okay, so this is the circuitry they have provided, and they have simply given that we have C, that is this main input is 0. Okay, C is 0. So I have numbered the gates 1, 2, 3, 4, 5, 6. We have total 6 gates. Let's solve from reverse approach. So we have output Y. Y is nothing but D and H whole bar, just numbered as equation number 1. Now you can see D. D is nothing but C bar here. D is nothing but C bar. E. E is nothing but A plus B whole bar. Okay. E is nothing but A plus B whole bar. Similarly F. F is nothing but A plus B whole bar, that is E plus C. G is AB. G is AB. And H is F plus G. H is F plus G. Simplifying further, we are getting it is as A bar B bar plus C plus AB. So we have all these outputs, right? We want D into H bar. Okay, D into H bar. D into H bar is nothing but D bar plus H bar. Okay, D bar is nothing but C bar whole bar because D is C bar plus this particular big term. So solving further, you will get that this A bar C bar plus A B bar C bar plus B A bar C bar plus B bar C bar. So B bar is 0, A bar is 0. So we are cancelling this term. So we are left with C plus AB bar C bar plus B A bar C bar. We know C is 0, just keep C is 0. So this particular term it gets cancelled. Next C bar is 1. Then we are left with A B bar plus A bar B. So A B bar plus A bar B. So this is nothing but XOR operation, right? XOR of A and B. So answer is option A, AB bar plus A bar B. Answer option A. Okay. Let's move to the question number 7. A bulb in a staircase has two switches, one switch being at the ground floor and the other one at first floor. The bulb can be turned on and also can be turned off by any of the following switches, irrespective of the state of other switch. The logic of switching the bulb resembles. Options are AND gate, OR gate, XOR gate and NAND gate. Before proceeding for the solution, you just see what they are telling. So basically we have one bulb and having two switches. They are kept in different floor. So basically we have to on the bulb, right? You have to turn on the bulb, and also we have to turn off the bulb using any of the switches irrespective of the state of other switch. We don't want the what is the state of other switch. Okay, we can solve like this. Let's say S1 is a switch which is at ground floor, S2 is at the first floor. So we want, if S1 is 0 and S2 is 0, okay, both switch are off, obviously bulb is off. But as soon as is S2, okay, is changing from 0 to 1, your bulb should be on. Okay, or for example, if your switch 1 is on, okay, so bulb is on, and that time your switch 2 is off. Once I change the switch to from 0 to 1, okay, just I put the switch 2 as on, the state of this Y, that is bulb, should change. So bulb was earlier on, so it is getting off. So that is the main thing you have to look into. Okay, we have considered all the cases. If one of the switch is off and second switch we are just turning from 0 to 1, that is we are making on, immediately bulb's condition is changing. It is off earlier, it is getting on. Okay, same for this case. So if you see the truth table closely, it is nothing but our XOR gate, right? So see, for 0 0 it is 0, 0 1 it is 1, 1 0 it is 1, 1 1 is 0. So whenever, if you see both the inputs are 0 or both the inputs are 1, it means if it is same, it is giving output 0. So this is nothing but the truth table of XOR gate. Okay, so as I mentioned here, if both are off, just if you are making one of the on, bulb is, we have to change the bulb to on. If both are on, if you just make off, bulb should be off. Okay, so option C, this is nothing but XOR gate. Let's move to question number 8. For the logic circuit shown in the figure, the simplified Boolean expression for the output Y is 0, A, B, C. So basically they have given a circuit where we have to find Y. What is exactly value of Y? We'll follow our regular approach, just numbering the gates and giving the output as some nomenclature D, E, F, G, like that. Let's solve one by one. G is nothing but NAND of AB. It is AB bar. D is nothing but G B bar whole bar. Okay. E is nothing but D B bar whole bar. F is nothing but D plus C bar. We know what is Y. Y is nothing but NOR of two inputs. Which are they? E and F. So Y is nothing but E plus F whole bar. What is E? E is nothing but, here you can see, D into B bar whole bar. Okay. E is nothing but D into B bar whole bar. So simplifying further, F D plus C bar whole bar. If you see over here, if we have A plus B whole bar, what we are doing? A bar into B bar. Similarly, here already we have bar, so it get cancelled, plus changing into the AND operation, and here D plus C bar as it is. So just simplify further, DB bar into D is nothing but DB bar, DB bar into C bar, DB bar, C bar. If you take DB bar common, you will left with 1 plus C bar. And you know 1 plus anything is nothing but 1. So 1 into DB bar is DB bar. Okay. So finally we get Y is nothing but D into B bar. What is D? D is G B bar whole bar into B bar. So simplifying further, we get G bar into B bar. Okay. But we know what is G AB whole bar. So AB whole bar and its bar. Okay. So bar get cancelled. AB into B bar. AB into B bar is nothing but 0 because we have B and B bar in multiplication. So answer is 0. Option A. Let's move to question number 9. Which of the following Boolean expression correctly represent the relation between PQR and M1? Okay. So M1 is output. We have to just see what it represent in the form of those gates, right? For example, option number A, M1 is P or Q XOR with R, P and Q XOR with R. P nor Q XOR with R, P XOR Q XOR with R. So before solving, you can see, if you closely see the options, XOR R is the common term. So this is R, this is XOR gate. So whatever we have to solve is Z. Okay. So we have to just see what is Z in terms of P and Q. We have P and Q. What is Z in terms of P and Q? And that will be our answer. As usual, we have numbered the gates. Outputs are X, Y, Z for the respective gates 1 to 3. See, X is nothing but P into Q bar. Y is nothing but P plus Q. Z is equal to X into Y. You can see is AND gate. So just put the values of X and Y in Z equation. X is nothing but PQ bar. Y is nothing but P plus Q. PQ bar nothing but P bar plus Q bar. Here PQ. If you multiply completely, you will be left out with P bar Q plus Q bar P, as those highlighted terms will be cancelled. Is nothing but XOR of P and Q. Okay, we have got Z as P XOR Q, and we know M1 is nothing but something operation XOR with R. Okay, so we have M is nothing but P XOR Q and XOR with Z. So option D. Okay, let's move to question number 10. The output F in the digital logic circuit shown in the figure below is, so we have F as output, we have AND gate, XNOR gate, XOR gate. We have to see what's F. So those are the options. F equals to A bar BZ plus AB bar Z, A bar B bar Z plus AB bar Z, A bar B Z bar plus AB bar Z, and A bar B Z and AB bar Z bar. Okay, let's solve this. So output of first XOR we have numbered as C. Output of this XNOR we have numbered as D. So we will solve C and D first. So C is nothing but A XOR B, nothing but A bar B plus AB bar. D is nothing but C XOR Z, that is C bar Z bar plus CZ. F is nothing but the multiplication of these two. We have C and in bracket D we have this term. Okay, so C bar Z bar get cancelled. We left with CZ. So F is CZ. We can simply keep C in our expression F, A bar B plus AB bar into Z. So we are left with A bar B Z plus AB bar Z. So which is nothing but option A. Okay, let's move to question number 11. A universal logic gate can implement any Boolean function by connecting sufficient number of them appropriately. 3 gates are shown. Okay, so first see the options. Gate 1 is universal gate, gate 2 is universal gate, gate 3 is universal gate, and none of the gate is universal gate. So before solving the question, let's see what question indicates. So F1 is output of gate 1, they have provided OR gate. F2 is output of gate 2, which is OR gate but one of the inputs is inverted. Third last is gate 3, which is nothing but simple AND gate. So we have to see which option is correctly resembles. Okay, let's solve this. So gate 1 and gate 2, if you see, right? Gate 1 and gate 3. Okay, these are the basic gates. Okay, so we know if the gates are basic gates, right? So we can't say that basic gates are universal gate. So simply gate 1 and this particular gate 3. So those are not universal gate. So simply we are rejecting the option A and C. Okay, because why these gates are not universal means using these basic gates we can't implement all the gates. Suppose I have given you OR gate or this particular AND gate, right? So you can't implement all other logic gates, right? NAND, NOR or XOR like that. But if we have the universal gate, for example we have NAND or NOR gate, these are universal gate, we can implement all the other gates using this. So we are rejecting simply option A and option C. Okay, so guys, yeah, that's about the second video of this digital electronics playlist. Thank you for watching our video. Please like, comment and subscribe to our channel VLSI Point.